Welcome to our presentation of Industry 4.0 and Internet of Things applied to nitriding, nitrocarburizing, and vacuum heat treating systems. You may have seen this slide or this citation from The Economist probably before. It dates back to 2017. For us, heat treaters or builders of equipment, it has been a fact that data is at the center of our business. We have started documenting information, metallurgical results, experiment results 30 some years ago. And most of those records exist and most of those records are used today. Of course, we have moved away from paper chart recorders to paperless chart recorders to encrypted log files, but data collection continues and is essential because it is needed for quality control, documentation of processes, as well as maintenance and troubleshooting. Some of the companies do use clouds, others don't because of other concerns such as security or data sharing. However, it is interesting to always have a off-premise secure server or storage that allows a company, in case of, let's say, fire or some other issue, to have a backup of all the data and the log files. This is especially important in aerospace, where records have to be well kept forever. We have also noted, in agreement with The Economist, that our service calls are related to software, diagnostics, and log files. This is all data. This is not really hardware. And even hardware problems are diagnosed via data analysis. So we need this data in order to troubleshoot any system worldwide, unless it's something very obvious, such as a broken bearing or a motor making noise. But this is rare. Actually, most of the time, it is a problem related to either electronics or sensors or software. The Internet of Things has been a growing trend since many years. Today, we are pretty much interconnected at every level, and it starts with our smartphones in our pocket, who usually are capable of providing our location even unwittingly. Those telephones also will help you when you try to drive somewhere and will tell you that traffic ahead of you is congested and will suggest a new route. And this is part of the Internet of Things, but is also part of a growing trend in artificial intelligence. Industry 4.0 is a huge buzzword since perhaps several years already, but in essence, it relies on smart network and smart machines. To better explain what it is, really, we have to go back to what was the first industrial revolution. Well, it relied mainly on the first steam machines, anything that was powered by water, steam, and allowed the first factories to emerge. The second industrial revolution, perhaps 100 years later, occurred when electrical energy started being used around the world and changed manufacturing entirely. There was a third industrial revolution, again about 100 years later, late 60s, early 70s, with the first computers. Those computers evolved more and more and eventually gave place to what is today the Internet of Things. The fourth industrial revolution doesn't look at individual machines, but really groups of machines or networks of machines which are smart, which are interconnected, and which allow to first collect that data, but also to interpret data, to learn from this data, analyze the data, and take actions by themselves. So they allow, among other things, actions such as predictive maintenance, where not only you do preventative maintenance every so often because you know a certain part has to be replaced, but you also can predict based on the current data that you're collecting that something is going wrong and very soon there'll be a problem. So you actually can fix the problem before it actually occurs. And this fourth industrial revolution also holds the promise of a different way of approaching or thinking our manufacturing systems, and also a different reality for humans. So it is a groundbreaking change. The current trends that indicate that the Internet of Things becomes more important have been long in the making. Actually, they stem mostly from the necessity to keep quality control, to keep quality assurance systems, to document. All of these require a huge amount of data, which is taken from each run, every furnace, every piece of equipment, and has to be somehow collected. It was extremely costly, still is very costly, to run a quality control department to address all of those issues. And this is where actually digitalization is of great help. It is not the necessary evil, but it's actually a great help because it reduces cost and allows for a comprehensive look, statistical analysis, troubleshooting of systems without spending as much time or money as we did before collecting all the data and trying to figure out and manually sort the data for every batch or run, and then have files and paperwork that goes along. This time we have basically a system that follows piece by piece every batch or every part going into the system and allows us to digitalize everything that has happened to this component. The following is a selection of what future holds for us next, or perhaps not future, because the automated machine learning is already here. Augmented intelligence or human-centered partnership already exists, and you have this idea of smart machines, smart robots, but also robots or machines that collaborate with humans. Those are actually called cobots. There are many more buzzwords that may not apply perhaps in heat treating, but are interesting nevertheless. Basically, artificial intelligence or augmented intelligence used in embedded in Internet of Things, endpoints, gateways, and edge devices are also in the making. Perhaps in the future, what we'll see is what we call quantum computing, and this is another advance in computing, and it may bring another perhaps almost revolution or revolution within Factory 4.0. The rationale behind developing an industrial Internet of Things platform for heat treaters has been around for a while. First of all, we all do, probably from the quality point of view, process documentation. We have accumulation of documented process recipes, log files, lab results, PPAPs, and this is actually a base for machine learning and artificial intelligence. Once fed or once taught, a neural network can be an extremely powerful tool for recipe creation and troubleshooting, customer support, or maintenance. There is a huge demand, it's growing, that's fueled by automation, quality control, and lack of qualified personnel or personnel willing to actually work in the heat treat industry. Globalization, together with travel restrictions, actually also promote the idea of the industrial Internet of Things because it can remotely solve problems without actually human intervention at all. And the implementation of the newest technologies, such as machine learning, artificial intelligence, and augmented reality, is expected to reduce costs. This slide shows a visual idea of the cost of having the industrial Internet of Things installed on premises or using cloud computing. Maybe several of you went through the same experience. Well, on premises, it appears that we look only at the cost of the software licensing. On the other hand, we also need to spend lots of time on customization and implementation, on hardware and maintenance of hardware, which becomes obsolete very fast. IT personnel that's actually formed for this type of hardware, maintenance, as well as training or retraining. On the cloud, you have relatively high upfront subscription fees. However, the implementation, customization, training, as well as IT maintenance remain much lower when you look at the cost that we incur inside a company. This slide illustrates an example of an infrastructure of an Internet of Things platform. Internet of Things platform is actually a multi-layer technology that enables management, monitoring, automation of connected devices within the Internet of Things universe. But as such, it must be adapted to each situation. In the heat treating world, we have on the shop floor many pieces of equipment, usually not from the same manufacturer, equipped with different PLCs, computers, process controllers, and they all must find a way to communicate with the gateway. For that, every piece of equipment has to be fitted with a protocol adapter that allows it to speak the same language as the gateway. Once this is done, data is being sent, processed, and stored. It is also shipped out, crunched in the aggregation section, and from there it goes onto the cloud gateway. Now, the cloud gateway is maybe a physical device or software actually, or both, that serves as a connection point between the cloud and controllers, sensors, and intelligent devices. It can provide additional security for the Internet of Things network and the data it is transporting. Once data has entered the cloud, it is being processed, reported, stored, and sent to the component which includes machine learning. This machine learning component basically is being taught first how to react and then starts coming up with models, solutions on its own. Those models are sent back to the shop floor or the on-premise infrastructure. Time series prediction is actually at the center of machine learning. For most of you, it's probably known for quality systems and statistical analysis. It was also part of models such as modeling for weather reports, for prediction of weather forecasts, and it is used as well for the behavior of machines, for predictive maintenance, and other aspects of operations. It relies also on what we call a long short-term memory, which is an artificial recurrent neural network architecture, which is used mostly in the field of deep learning. The advantage is that the long short-term memory networks are very well suited for classifying, processing, and making predictions based on those time series data. Why? Because there can be lags of unspecified unknown duration between important events in time series. And in our case, as heat treaters, we may be running or not running a piece of equipment. However, once you put together all the information you have, all the data, regardless of time, however, by sequences, you start realizing that there are trends. Machine learning or deep learning is difficult to describe in one short slide. It relies on neural networks, and the description of neural is based on the analogy to the interconnections of nerve cells in our brains. It also tends to behave in a similar way by attributing relative values to the information, the data it receives, and data of high value is privileged while data of lower value is given a weight that is very low and may be dismissed, forgotten, or given lesser priority. It consists of input layer, output layer, and so-called hidden layers. Now, the input layer contains units or artificial neurons, which are receiving input from the outside world. This is where the actual learning on the network actually happens. The output layer contains units that correspond to the information that is fed into the system and also whether it learned any task or not. Hidden layers are hidden between input layers and output layers. The only job of a hidden layer is to transform the input into something meaningful that the output layer or unit can use in a way. Most of the artificial neural networks are all interconnected. And this means that each of the hidden layers is individually connected to the neurons in its input layer and also to its output layer, leaving nothing in between. This makes it possible for a complete learning process. And also learning occurs to the maximum when the weight or the importance inside the artificial neural network get updated after each iteration. Current mainframes can map up to 30 layers with millions of interconnected artificial neurons. Analytics are somewhat related to the previous idea of machine learning. The sophistication level basically at the beginning you have the basic collection of data and you have your production data, production statistics, information that has been gathered by data aggregation or data mining, but let's say it's mining within your own heat treat plant, right? So it's just collecting and it's not really sophisticated. This is what most of us do to some extent. We do collect data and we do make those charts showing, hey, what's the machine that gives us much more trouble, the one that is least performing, the one that has more downtime or has the wrong energy consumption. Now, it becomes a bit more complex when you start to find diagnosis, because well, the question here, why did it happen? So once you have those anomalies or those curves or those statistics that pinpoint some issues, you have to ability to read time series data and to pinpoint what caused failures. This is a bit more complex. Based on this, and this is again feeding back into this learning ability, machine starts to learn and be able to forecast. So this time, when it collects data, it actually collects data looking at specific problems, such as excessive current or excessive electrical consumption on some kind of motor, some kind of pump, some kind of furnace, showing that perhaps there is an issue that will lead to failure. So it is predicting or looking at specifically focusing on specific issues. And this focus is reinforced from incoming data. So the more it collects data, the more it collects data on failures, the more it is fed back and goes through several input and output layers and in between layers to analyze and really bring out the essential issues in a plant. The next step up is this prescriptive analytics, and this prescribed maintenance really is also focused maintenance. So today we have obviously this preventative maintenance, which is based on our experience. And in a sense, let's say that we can compare our industrial Internet of Things and Factory 4.0 to a very old and experienced maintenance manager who knows what will go wrong, knows which machine, which part of a machine, which component is probably going to fail. So it's a question of experience, but in this case, let's say that our maintenance manager has retired and it's difficult to find another one who's experienced, or he's spread very thin because we don't have many people in our plant. So this basically allows you to produce this prescriptive analysis or analytics are capable of predicting schedules and dictating preventative measures that will keep a plant running without any unscheduled stoppages. This slide actually repeats some of the notions that I described before. One of the important ones, actually there are two, are anomaly detection and process model or process simulation, which I'll talk more about in the next slide. One of the issues that we do have on a daily basis is that the more you automate the systems, the less employees you do have. And at the end of the day, you do have printout log files, data from every process run on a daily basis. So there aren't enough people, perhaps, to analyze and go in depth over each log file. And many times, very strange behavior by equipment or unexplained behavior may go unnoticed unless there was a major metallurgical fault, but you wouldn't know about it if you didn't spend time monitoring your log file. So log file analysis takes time, takes resources, and is a great way of seeing what goes wrong in equipment or in the recipe. And this may have to do with the calibration of analyzers. It could have to do with the type of load, with the type of flows chosen, but essentially you would need to see what doesn't really make sense and analyze this. It takes a bit of skill. Maybe see the data as a table, maybe see this data as curves, to really pinpoint the nature of the problem. And for me, one of the foremost advantages of having this interconnective Internet of Things and smart control systems is the ability to pinpoint anomalies. And believe me or not, but there are quite a few in a heat treat operation, except some of them do go unnoticed because people simply run out of time. And if the results are okay, well, they're okay, but you don't see the trends in a long time. And this goes also with statistical analysis. For instance, if you were to run a very simple nitriding process or for nitrocarburizing process over several months or years with fixed flows, you would be surprised that the results suddenly changed after you have put in a new fixture, or that over the course of time, it seems like the specifications are not achieved because over years and years or days and days, it seems like your white layer gets thinner or diffusion layer changes. And this is a trend that you can see only if you compare log files that go back perhaps a few months. And this will indicate what? It indicates perhaps that your furnace is getting contaminated. Perhaps it indicates that your flow meters or mass flow controllers need calibration. It may indicate many things, but you won't find out until you're really out of spec and the load of parts that you have treated is being rejected by a customer. So it is interesting because it takes a skilled maintenance person, perhaps a metallurgist or a heat treater to find the root cause. And there is really nothing that warns people in advance in systems that aren't smart, unless you spend every day hours analyzing and compiling data and making statistics from each piece of equipment, which is not only painstaking but is very costly for the company. This is a very short illustration of really what this anomaly detection looks like from the machine point of view. So basically our machine will look at the sequence of dependent or interdependent process values, and do they appear improbable? Are they out of place? And do they deviate from limits or averages? And this will actually sound the alarm for the operators or people, maintenance people and process engineers to look closer at the system. This slide shows the learning path of anomaly detection. It's a very simple graph showing in blue what was the set point in 2 stages of a process of nitriding potential. So what you see is that it was never reached. The blue line has never been reached by the red line, which shows the actual reading from the gas analyzer. And this brings many questions, because in order for the machine to be able to pinpoint the problem or the most likely problem and try to solve it, it must receive structured data that show how it was diagnosed before by humans. So the question is, were the flow meters having problems? Analyzers were out of calibration. Something else was out of calibration. Was there a huge variation in load size or active surface? Was there a concern of contamination? So this data actually must be structured and fed into the system so the deep learning can take place. As a probably heat treater, if you ever tried nitriding or nitrocarburizing with fixed flows and the same load every day, you probably see that over the time ammonia flow remained the same, and strangely enough, white layer gets thinner and thinner and thinner over time. It could be a question of accumulation of contaminants, and it could be also proven that dissociation was increasing in the furnace or potential falling. And it's actually, this is the way you teach a system, intelligent system, uh, how to react and how to be predictive. This is an illustration of how a process simulation and modeling actually work. Um, it's um, um, it's complex, but essentially can be boiled down to fitment. Um, you can a system can select, and we can select. We did that at the beginning, but today basically a system which is using artificial intelligence is selecting the processes with the best fitting result that correspond to part specification as far as metallurgy goes. Um, or on the other hand, the choice is to select log files which are related to one specific component and one specific type of furnace, and assume that the majority will be within specification, which brings us to the next stage, what is machine learning or deep learning. The industrial Internet of Things offers many advantages from the point of view of asset management. As we are building a platform, we have to integrate documentation, technical drawings, data, upgrades, maintenance reports and activities, as well as consumption of energy and gas. Uh, all of this basically provides a cloud-driven connection to equipment with status and data available live on all connected devices. Now, this may also lead to what you call Internet of Things. It was invented, or perhaps the expression was invented by Carlos Nizam, who was working at Airbus Group. And what he did was basically to streamline all the activities in such a way that he was able to track physical assets throughout the company. And knowing the size of Airbus, imagine you could track all the airplane parts and tools. So if you apply this to a large heat treating operation or several plants that are operating simultaneously, you always know what is the status of all your assets. And this is an actually great piece of data for management, not only troubleshooting, and sort of is a byproduct of integrating an Internet of Things platform. There are several advantages of the industrial Internet of Things for a heat treater. First of all, you roll together all the existing components such as SCADA, remote control, process modeling in a model that basically is capable of working by itself. Also, you can predict and communicate needs such as TUS, SAT, and this based on a log file or usage, as well as a calendar. Also, you can learn, analyze equipment performance, and warn you of any possible problems. So you have this component of predictive maintenance. And this is one of the hot topics in most of the industry. And finally, you take out the guessing game out of process recipes, because the system is capable or would be capable of suggesting a recipe or a model to which you should adhere. The Internet of Things is also facing many challenges. The first one being connectivity. You have interruptions, blackouts, brownouts that affect ability actually to transmit data, and actually for even equipment to work in a continuous fashion. The second challenge is the lack of uniform practice, and this has to do with companies trying to get a share of this very hot new market of the industrial Internet of Things. Simply they develop different hardware specific platforms which are not necessarily compatible with each other. The next one is probably the most obvious one: the security, data, safety, privacy, intellectual property, and other factors. Many of our customers, and this is worldwide, do have confidentiality agreements, have to respect legislation such as ITAR, and that makes sharing outside a company or outside a locked system very difficult. There is also a lag between expectations and deliverables. Many people expect that this industrial Internet of Things will be able to fix many problems. It potentially can, but also it is a relatively long and tedious process, similar perhaps to one on putting together an ERP or a CRM for a large corporation. And finally, and that will take us to the next slide, the human role in machine learning. It may come to you as no surprise that one of the biggest limitations in the industrial Internet of Things is the human factor. The time series prediction is interesting, nice, and used really across the industry. It relies on long short-term memory, but it needs teaching by humans. And also it needs a pre-structured amount of data. This data very often is missing. Then it requires very long offline batch training involving humans again. It does not learn in an incremental way or in an interactive way in real time. There is a poor transfer of learning ability from one piece of equipment to the other, and modules. Integration is relatively difficult. And debugging and correcting the industrial Internet of Things and its databases, its neural networks is again taking a huge amount of manpower. The industrial Internet of Things raises the same questions as we have every day regarding privacy, confidentiality, and security of our own data. It goes from our own private smartphone to our banking over the internet, etc., etc. Obviously, exactly like our smartphones and perhaps self-driving cars, it also makes life easier and perhaps also spares some of the expenses that are currently associated with heat treating, documentation, maintenance, and quality control systems. It is very encouraging to know that our new platform, which is being right now built since a year, will integrate existing elements such as the SCADA automation for lights out plants, metallurgical databases. So all of this information will be fully integrated. And obviously, I couldn't do this presentation without mentioning the current pandemic, which has modified and accelerated many trends in our society. And one of those trends is probably affects shopping, online shopping, online banking, and obviously we cannot do online heat treating, but the need for intelligent machines or intelligent plants is rising. And one of the reasons is that we all see that our service people cannot travel as easily, and we often travel worldwide to many countries. So we cannot travel, or if we travel, we need to quarantine. So interconnecting actually machines and being able to run diagnostics, to see reports, helps enormously in this evolving world because we believe that this trend or trends in technology that have started several years ago are definitely being accelerated in the current context. And I believe probably that it also holds many positive points for the future for heat treating industry by improving costs, improving management of resources, and streamlining operations. There are several conclusions, but the first one actually is privacy, confidentiality, and security. This is a major concern, and it is being addressed in many ways. You have systems that have a virtual intranet of things that does not communicate with the outside web. It communicates within an intranet that is secure within a company. The second idea is to keep all the equipment running, even though it's smart, running directly with controllers installed on the piece of equipment direct. So it is actually reporting, it may be archiving, it may be gathering data externally, but the processes are always being run locally. The second is that there is a promise actually, and this is expected everywhere, to lower costs. However, the systems must be tailored in a way that a clear path is established for specifications, expectations, and deliverable. And this means that a customer and the provider of a platform must know precisely where the system is going, where it starts and where it stops. It is very similar to a customer enterprise software platform, such as a CRM or an ERP. And obviously, this trend has been around for a few years, but in the current pandemic, all those trends implicating the internet and working online and working remotely have accelerated. And most likely, it is going to be the trend for a few years to come. Thank you very much for attending my presentation. If you have any questions or suggestions, please don't hesitate to call me or write to me at jack.kalukci@nitrex.com. Have a great day. Thank you very much. Stay safe. Goodbye.